Hello guys, this is Dallas here, and today, continuing Amazing Math. Now, with that out of the way, let's get into it. Prime numbers. Prime numbers are the building blocks of numbers. Number 7 is prime because it can be produced by the multiplication of only two whole numbers, 1 and 7. In other words, 1 and 7 are the only factors of 7. The number 24, on the other hand, is compost, not prime, because it has many factors. 1, 2, 3, 4, 6, 8, 12, and 24. The first few prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29, 31, and 37. Notice that 1, by definition, is not prime, and that 2 is the only even prime number. Connection. Rectangular numbers. If you arrange prime number of pennies in rows and columns on the table, you can place the pennies all in a row, but you cannot arrange them into any other rectangle. Fractions. Today, we express parts of a whole in three different ways: through fractions, decimals, and percents. However, if you were doing math in ancient Egypt or ancient Greece, you would have worked in fractions only. Decimals and percents didn't really catch on until 1,000 years later. Adding and multiplying fractions can be tricky. Here are a couple of activities that will help you see the concepts behind adding and multiplying factors. Wait, what? Oh, fractions. Multiply fractions. You do not need a common decimeter to multiply fraction. The Fibonacci sequence. Figure what number comes next in the following sequence. 0, 1, 1, 2, 3, 5, 8. Blank. Did you figure it out? The next number is 13. Why? Each new number is the sequence of the sum of the two numbers before it. To find the next number in the sequence you needed to add the two previous numbers, 5 and 8. Here's the sequence with a few more numbers. 0, 1, 1, 2, 3, 5, 8, 13, 21, 20, 34, 55, 89, 144, 233, 377, 610, 987, 1,597, 2,584, 4,181, 6,765, and next. This pattern of number is called the Fibonacci sequence, after a nickname given to a man named Leonardo of Pisa. He was an Italian mathematician who included it in a book he wrote in the year 1202. The nickname is short for Fidelius Boncii, meaning son of the Boncii family. Golden ratio. Use a calculator to divide two constant numbers in a frequency sequence. For example, try dividing 13 by 8. Now try dividing larger consecutive numbers into sequence. Do you see a pattern? The results of these divisions are all slightly greater than 1.6. As you divide larger and larger pairs of numbers in the Fibonacci sequence, the ratio is even closer to 1.61803. Closing in on a special number. This number is called the golden ratio. It is one of the few numbers lucky enough to get its own Greek letter. It is often referred to as phi, pronounced phi, and rhymes with pi. The Greek letter looks like this. The golden ratio has fascinated people for centuries. For example, some artists and artists use it in their work. They may design a rectangle 5 times as wide as it is tall, a so-called golden rectangle, because they think it has a pleasing shape. Numbers and counting. The golden ratio has been called the diving population. People have searched for the golden ratio in all sorts of places. In the dimensions of the human body, the spiral of a shell, even in patterns in the stock market. Historians have looked for the golden ratio in famous paintings like Mona Lisa and in the design of ancient Greek buildings. No one knows for sure whenever the golden ratios found in these places are there by chance or if they're deeply included, but it is fun to guess. Angles. Two lines that meet at a point form angles. Angles are used everywhere. Carpenters use angles to cut wood accurately. Civil engineers use angles to construct roads. Astronomers use angles to locate stars in the sky. Angles are a way to measure and describe shapes. The angle you see the most in acupuncture is 90-degree angle, called a right angle. The ancient Egyptians who built the Great Pyramid of Giza used to make accurate right angles in the pyramid's square base. How did ancient Egyptians measure right angles? No one knows for sure. Maybe historians believe they used a triangle made of rope. Parabola. When you toss a ball in the air, the path it takes is a very graceful up and down curve called a parabola. This remarkable curve appears in many places, in nature and many objects made by humans. It is the shape made by water streaming out of a drinking fountain, as well as the shape of the cable on a suspension bridge. When you stir a glass of water, the surface of the water formed a concave shape called a paraboloid, which is a three-dimensional version of a sensitive microphone of parabola. Telescope mirrors, satellite dishes, and reflectors on super-sensitive microphones all take the form on paraboloids because they are able to reflect the waves coming from far away to a single point, called the focus. Eclipse. The Earth travels around the Sun in an orbit that's nearly not quite a circle. In January, we are a little bit closer to the sun, and we are in July. The shape of our orbit is an ellipse, which is the mathematical term for oval. The Earth not only has an elliptical orbit, but also has elliptical shape bulging in the middle. If you cut the Earth in half from pole to pole, you'll see an elliptical cross section. The easiest way to see an eclipse is to hold a glass of water at an angle. The surface of the water forms an ellipse in the glass, hiding a cone. What does a parabola have in common with a circle and an ellipse? All three of these curves can be made by cutting a cone in different ways, called conic sections: ellipse, parabola, hyperbola, and, well, circle. The old German town of Königsberg had different bridges. It had 7 bridges connecting 2 islands and the shores of the river Pregel. Leonhard Euler was a great mathematician. Was given the problem of determining whatever it was possible to take a walk that crosses each bridge only once. Here's a simple map of the bridges of Königsberg. Try drawing a path that crosses each of the 7 bridges only once without lifting your pencil. Give up, no surprise. The task is impossible. Most likely, the citizens of Königsberg tried to solve the problem through time to a suspect. The search for a solution solves the problem enough times to suspect that the search for a solution was hopeless. Why was Euler interested in a seemingly simple problem? He was an important mathematician. The head of the mathematics department of St. Petersburg Academy of Sciences. Euler recognized that this was a completely new type of problem for mathematicians. Through his work on the problem, Euler created a totally new field of mathematics that has a wide range of applications today. The techniques used to solve problems like this one are crucial to analyzing internet connections. They are used to find the shortest route between points, analyze traffic flow, design printed circuit boards for electronics. The problem of Königsberg's bridges is made easier if you draw a very simple diagram, essentially a stick figure. Instead of drawing islands and bridges, we draw dots with lines connecting them. Each dot is called a vertex. Is a landing place, while each line, called an edge, is a bridge. This diagram, called a network or a graph, once you have a graph, you don't even need the underlying map. The graph shows the important relationships in a simple way. Graphs can represent just about any connection you want. For example, the vertices can represent individual students in the class, and the edges can show their friendships. Can you connect 9 dots with 4 straight lines? Drawing 4 straight lines that connect these 9 dots without lifting your pencil from the paper. See page 131 for the solution. Likewise, the vertices can represent individual websites as while the edges can show how they are connected on the internet. In this way, the lessons we learn about one network can apply to other very different networks. Lessons we learn about one network can apply to the other very different networks. Euler discovered a simple way to prove the impossibility of crossing each of Constant-Berg's bridges only once. Only once. On a single walk, his solution revolved around looking at each vertex and seeing how many edges were connected to it. Will always come in pairs, with one edge representing your trip to the place and another symbolizing your trip away from it as you continue your journey. Therefore, vertices in the middle of your walk must have an even number of edges touching them. While only 2 vertices, one each at the beginning and end of your walk, can have an odd number of edges. Look at the graph of bridges again. Only 2 vertices, one each at the beginning and end of your walk, can have an odd number of edges. Look at the graph of the bridges again. More than 2 vertices have an odd number of edges connecting them. This is a clear sign that crossing all the bridges only once is impossible. Here are other puzzles to try with this method. Can you draw a box with an X in the middle without using your pencil? What about this? Box with a roof on it. See page 132 for the solution. Random walk. At the lake of by my house, children play a game on a raft. The game starts with 2 people in the middle of the raft, facing each other. Then they play a game of rock, paper, scissors. The loser of the game has to take a step backward. The children continue playing rock, paper, scissors until someone backs up so far that they step off the raft and fall into the water. You can also play a solo version of this game right at home by flipping a coin. Determine where on the ground the ends of your raft lie. And then start flipping. If your coin shows heads, take 1 step forward. If your coin shows tails, take 1 step backward, depending on your outcome of your flips. You may end up in the water sooner rather than later. It is more likely, however, that you'll move back and forth for a while. Since your steps are random, this is called a random walk. This may sound like fun and games, but to mathematicians, it's serious business. Entire books are devoted to the properties of random walks. Random walks are important because many real life style systems behave like them. For example, molecules in a gas or liquid are knocked back and forth randomly by other molecules. So you can think of one molecule being on a random walk. When molecules move randomly through material, this process is called a diffusion. You can see a diffusion in action if you carefully place a drop of food coloring in a glass of water. At first, the color is concentrated in the place where you drop the dye. Slowly, however, the dye spreads out until the entire glass of water, same color. The molecules of dye are traveling in random walks. And that for today. Hope you guys enjoyed, and I'll see you again very, very soon. Later.